our last official lecture in statics. So we are finishing the material that I wanted to cover in chapter 8 about friction, and then we're going to do a little short review for the final exam, just to prepare you for that. The content of the final, and the structure of the final, rather, not the content, but the structure of the final and what you're allowed to bring to the final is identical to the midterm exam. So there will be 4 problems. You get a study sheet, calculator. You have to give me all your paperwork at the end and so forth. If you're out in the cyber land, you need to get a proctor or work with me to proctor you. Final will take 2 hours. And at the end of the period today, I'll give you the 4 problems that will be representative of what you can expect on the final so that you'll be ready to go. All right, so when we take a look at our web page, our Moodle page, you'll see that I've posted statics lecture number 30, which begins chapter 8 on friction, and today we're going to do the last lecture, 31. So instead of actually covering new material, what I would like to do is to work a problem that sort of illuminates some of the issues that I would like you to think about when you're considering friction. So to that end, I'm going to come over, and you can tell it's the end of the semester because I've completely run out of paper, and so I'm using like leftover paper, leftover periodic tables and so forth. So, but I'm going to put I put a piece of paper up on the document cam. All right, and we're going to work a problem. We're just going to work one problem today, and then I'll assign you one more problem in the homework, and then that will be the last homework assignment that we will have in this class. The other thing is that, as I said, this will be the last formal lecture, but for those of you on campus, I will be available Monday at this time, so if you need me, please find me. And also, if you are not on campus, or if you are on campus and you prefer to communicate personally, please send me an email and we'll set an appointment. All right? So let's take a look at some of the problems at the end of section 8.2. And we're going to look at problem, let's take a look at problem, there are 2 good problems. There's 848 and 856. So I'll go ahead and do problem 848, and then for your homework, I'll ask that you do problem 856. All right, these problems involve something called a wedge, which is like a sliver of wood that has, or sliver of something that has a different angular relationship other than rectangular, square. So for example, you'll see here on problem 848, we have a little wedge of wood underneath this structure. All right, and similarly, when you work problem 8.56, you'll see that there is an angular relationship here between the contact of the blocks. The thing to remember in each of these is that the friction at that contact surface is equal to a coefficient of, if it's moving, dynamic friction, or up to the coefficient of static friction times the normal force, and that the normal force is always directed normally or perpendicularly to that surface of contact. So those are sort of the factors that you need to bring into your analysis. So here on 848, we have a machine part ABC. And basically what we have is something that is hinged at point B, and it has sort of a lever. And this sort of comes down like that, I guess would be the best way to draw it. And then over here at C, at point D on the ground, or C on the machine part, there is a contact here. Okay. So it sort of looks like this. All right. Now, this line does not actually exist. That's just a single That's just a smooth surface, and that's just a single part. All right? But what happens is at this wedge, we are told that this angle of contact, or this angle of the wedge, is 10 degrees, that we push on the wedge with some force P, and that we push here on point A with some force of 600 newtons in the horizontal directions. All right.
It's kind of like if our thing was a spring and
yes,
pulling it down.
Exactly. Exactly, right. Or perhaps there's something uneven here, and so you're wedging it, like if you go to a restaurant and the tables are all wonky, and you take little sugar packets or napkins and fold it up underneath, that's sort of the effect that we're looking at. Good question. All right, so the problem says that the machine part, ABC, is supported by a frictionless, so there's no friction here at B, and a 10-degree wedge at C, knowing that the coefficient of static friction is 0.2 at both surfaces of the wedge, so that means right here, mu equals 0.2, and right here, mu equals 0.2. It asks us to determine the force P required to move the wedge to the left and the components of the corresponding reaction at B. All right, so what's really going on here? Well, what's going on is that if we push on P with a particular force, that there's a force acting on it right here, which is the normal force between these two, and there's a normal force acting on it right here, which is the normal force between the floor and the wedge. And both of those are going to have a maximum magnitude. When we talk about the coefficient of static friction, we know that friction will never cause something to move. Friction always opposes motion in this type of a situation. You can think about causing motion when you have tires on a surface, but because if it wasn't for friction, the tires would just spin. But that's not really what I'm referring to. What I'm saying is that friction reaches a maximum based upon the coefficient of static friction and the normal forces. And it could be less than that, or it could be more than that. But when it or it could be up to that amount. But when it says to cause it to move, what we're talking about is impending motion. And so what that means for our analysis is we are going to be overcoming, P is going to overcome all of the forces at that particular, on that wedge, and cause it to start moving to the left. All right, so as always, the way we start is by drawing a good free body diagram. And there's two different things going on here, but we'll talk about that in a minute. We actually need to have two free body diagrams. One of them is on the machine part, and the other is on the wedge. Okay, and since it's impending motion, that means that the force of friction at either of these two contact surfaces is equal to mu s times n, which they call F sub m, or maximum frictional force. All right, so if we take a look at the wedge, let's see what's going on with the wedge. All right, the machine part is pushing down on it like this. This is the normal force from the machine part. And the floor is pushing up on it. That is the normal force from the floor. And force P is pushing over in this direction. And at impending motion, we can say that the force of friction at both of these surfaces is going to equal to mu s times n at that surface. All right, well, the force of friction on both the top and the bottom of the wedge opposes motion. So if we're pushing it to the left, that means that the frictional force is opposing it to the right, and the frictional force is opposing it to the right. So we have to overcome both of those frictions in order to make it move. All right, well, let's continue with what that means for us. Here at the floor, is this weightless? It doesn't have a weight on, does it? Okay, that's fine. So if we just set up summation forces x equals 0, right at that minute of impending motion, and summation forces y equals 0 on the wedge, what we find is that in the x direction we have minus p plus the force of friction on the floor plus the component of the force of friction, I'm calling it the machine part, okay, on the machine part that's in the x direction will equal 0. All right. Now, we also have a couple of normal forces. We have the piece of the normal force that's acting in the horizontal direction. So I'm going to think if they're going to take that into account. They're probably going to. So in order to determine that, here we're going to have the normal force between the floor and the wedge and acting down, the normal component of the machine part acting down, the piece of that operates in the y direction, and there are, the way I have it set up, okay, you're probably going to look at this and say, I get that. But the force of friction is actually going to have two components if I set it up this way. I could set it up perpendicularly to that, and I'm trying to think if I want to do that or not. I think I'm going to leave it like this. So I'm just going to have to include a couple of things. So this would be the piece, the force of friction. This one is purely horizontal. This is partially horizontal. And then we're also going to have a piece of the normal force that is acting in the x direction as well. And that's going to be positive. So the piece of the normal force of the machine part that's acting in the x direction. These four things have to equal 0 for impending motion. In the y direction, we have the piece of the normal. In both, we have the entire normal from the floor. We have the piece of the normal in the y direction. And then the way I have it set up, we're also going to have to take into account the piece of that frictional force that is operating from the machine part and that surface that's operating in the y direction. And those two things will have to sum to 0. All right, so we have part of our picture here, but we're not going to be able to determine the rest of the picture until we take a look at the machine part, and then we're going to have to resolve into vectors. Fortunately, we know that angle's 10 degrees, so it's really not that hard. Maybe I should finish that off before I do it. Let's go ahead and get my directions in here. All right, so back to the wedge. I'm just going to make these equations more usable. I have negative P plus the force of friction on the floor plus the force of friction on the machine part in the x direction. Well, let's think about what that is. This is 10 degrees. This is the entire force of friction from the machine part. And so if I resolve that into y and x components, if this angle is 10, alternating interior tells me that this is 10 as well. And so it's the force in the x direction is going to be that times the cosine of 10 degrees plus the normal component from the machine part in the x direction. The normal is, let's go go ahead and draw this again. So the normal piece looks like this. That means that we have a y component and we have an x component. And so if this angle is 10 degrees, this is perpendicular to this. This is perpendicular to this. So this is also 10 degrees. So that means that my normal force is going to be in the x direction is going to be the normal force times the sine of 10 degrees. 1, 2, 3, 4, and those 4 things are going to have to equal 0. All right, now the other part of it is we know that for impending motion that the force of friction is equal to mu s times n. So what that means is that when we have frictional things, we can write them in terms of that normal force, and it'll just eliminate one of our variables. So for the wedge then, to finish this off, we get negative p plus mu s, which is 0.2, times the normal force from the floor, plus mu s times the normal force from the machine part times the cosine of 10 degrees, plus the normal force from the machine part times the sine of 10 degrees. And all those things added together equals 0. Okay, so this is unknown. This is 0.2. This is 0.2. These two are both unknown at this time. And this is just one of those. So I could actually combine those two just to simplify, because I have the normal force of the machine part. So I have it times the cosine plus the sine. But I'm just going to leave that alone for now. So we have our first equation as explicit as we can make it at this point. All right. Now, in the y, this is summation forces x equals 0. Then we're going to get summation forces y equals 0 on the bottom, on that wedge. And so we get to rewrite the normal force from the floor minus the normal force MPY plus the frictional force from the machine part in the y direction equals 0. And similarly here, let's go ahead and draw the top of the wedge. This is 10. This is the normal force from MP. This is my y component. This is my x component. So if this is 10 degrees, this angle is also 10. So my normal force from the machine part in the y direction is MP times the cosine of 10 degrees. And my frictional force is that normal force times mu sub s equals 0. All right, so here I have two unknowns, but here I have three unknowns. So I have three unknowns and two equations, and I can't solve that, can I? It ain't possible. All right, so I need to look at the machine part next. But I do have two equations that are pretty explicit. They're as explicit as I can get. The only thing I could do really is change this just to 0.2, because I know that that mu sub s is 0.2. All right, so now let's look at the machine part. What we're looking for is, what is that normal force? Okay, so if we do this and we draw this because it's on the wedge, we know that there's a normal force between the wedge and the machine part. This is really drawn badly. I'm gonna have to get a better picture here. There. All right. So the normal force of the machine part is pushing up like that. There's a reaction at B in the x direction, a reaction at B in the y direction, and a 600 Newton force pushing right here. So we need to figure out what this is. Well, first of all, we know that this angle is 10 degrees. So that means that we have to resolve that normal force of the machine part into the normal force of the machine part in the y direction, which is going to be positive, and the normal force of the machine part in the x direction, which is going to be negative because the arrow goes like that, right? So there we go. So then let's take a look. Summation forces x equals 0 on the machine part. We have 600 newtons plus RBX. And in the x direction, this is negative minus the normal force of the machine part in the x direction. And then similarly, if this wants to move this way, the frictional force is going to be looking this way. So we're going to have, in the x direction, it's going to look like a plus, which is kind of weird, but there it is, just the same, plus the frictional force from the machine part in the x direction. And those four things added together are going to equal 0. Then in the y direction, these are both x, so all we have is RBY. But then we have plus the frictional force of the machine part in the y direction. And in the normal direction, we are also pushing up. So that's plus the friction from the machine part in the y direction equals 0. And at that point, we have 1, 2, 3, 4 unknowns. We can, friction part, I'm sorry, this should be the normal. I've got this normal. I just wrote n twice, like that. All right? All right, so now, in order to get some solution to this problem, we're going to have to do a summation of moments on this machine part. There's a couple of choices we could make. If we put a pin right here and do the summation of moments of these other forces, that would be great. Or we could put a pin here, and we could solve for RBY pretty quickly because RBX is collinear. So we would just have the moment from this and the moment from this. So let's try that, just because the geometry is a little bit easier if we do that. Okay, so we're going to take the summation of moments about point C, set them equal to 0. So we have the 600 Newton force is going to spin it clockwise, which is negative. And since that's a horizontal force, we need the vertical distance, which is 200 millimeters, or I would just say 0.2 meters. This is collinear, so it's not going to produce a moment at all. But RBY, the way I have it drawn, will also produce a negative or clockwise moment. And since it's a vertical force, we need the horizontal distance, which the problem says is 250 millimeters, which is 0.25 meters, equals 0. So the good news is we can use that equation to solve for RBY right away and see if that simplifies any of our work. Okay, so we have 600 times 0.2, and that is negative 120 Newton meters equals RBY times that, so I could just take that and divide, and I'm going to get a negative number. And I get that RBY, that magnitude, is negative 480 newtons, which means I've drawn it incorrectly. Well, if you think about this, that makes sense, because really RBY is going to be pulling the machine part down, isn't it? It's not going to be pushing it up. It's in tension. Yeah. Yeah, actually. Well, it's just the sign here. It's just that it means I've drawn it incorrectly. In other words, I've assumed it to be positive, so when it comes out to be negative, I know that it really looks like this. See, yeah, so it's 480 newtons. All right, so at that point, I want to go back and take a look at the machine part in the y direction, which is right here. And I'm going to write this equation and see if I can solve for anything. So now I have negative 480 newtons, that's my RBY, plus the frictional force of the machine part, between the machine part and the wedge in the y direction, plus the normal force of the machine part in the y direction. Those things together equal 0. All right, well, I know that the frictional force is actually equal to mu s times the component in the y direction. Oh, see, I got a problem. No, it's okay because I'm in the y direction. It's good. That's my friction in the y direction between the machine part plus that normal force, the machine part in the y direction equals 0. And so what I see is I know this value is 0.2, and so I can actually factor that out, right? Because this is 0.2 plus 1 times that normal force on the machine part in the y direction plus negative 480 equals 0. So now if I just go back to this geometry, to the trig right here, I'm going to be able to solve for the normal force, and then things are going to get solvable in a hurry.
Oh, we can't factor it out because they're the same.
Exactly. Very good. All right, so let's go back to my wedge. Let's get my angles and find out what is that component in the y direction. Okay, this is 10 degrees. There's the normal force, the direction. Well, actually, it's this way on the normal force, right? And so if this angle is 10, this angle is also 10 degrees. So that means that the normal force in the y direction is the entire normal force of MP times the cosine of 10 degrees. I multiply that by 1.2, and then minus 480. And I can finally solve for the normal force on that of the machine, between the machine part and the wedge. All right. So to do that, I'm going to bring 480 over to the other side, and I get the normal force of the machine part times, let me just do this, equals 480 divided by whatever this is multiplied by. And then I get the normal force between the machine part and the wedge, and I can make that solution right now. All right, so I get 480 divided by 1.2, divided again by the cosine of 10 degrees. And that total number is 406.17 newtons. Well, that's good, because now I'm kind of getting somewhere, right? So we have a number. Oh my gosh, we actually have a number after all this time. Well, let's go back to my wedge equations. And here we go. So now in the y direction, or in the x, let's see, sine 10, p is an x. Okay, so on the wedge again, we're going to pick up both of these equations. We get negative p, which we don't know, plus mu s, which is 0.2, times the normal force between the floor and the wedge, which we don't know, plus mu s, which is 0.2, times the normal force of the machine part, which we now know to be 406 newtons, times cosine of 10. This is 0.2. It looks awful. There we go. Plus the normal force of the machine part, 406 newtons, times the sine of 10 degrees, all equals 0. And if I look at that, I have two unknowns, don't I? I have the normal force on the floor, and I have
Negative P.
negative P.
Should we find the force on the floor then?
Right. I think what we'll do next is we'll go to the equations in the y direction on the wedge. Because then we'll have the normal force on the floor. Let me do this. On the wedge equals 0. So the normal force between the wedge and the floor, we don't know yet. But we know the normal force between on that machine part, and we know when we multiply that by the cosine of 10, we'll get that component. Then we add to that 0.2 times the normal force between the machine part, which is 406, times the cosine of 10 equals 0. And look at that. We're ready to solve for the normal force on the floor. That's going to equal 406 times the cosine of 10 minus 0.2 times 406 times the cosine of 10. And so the normal force between the floor and the wedge is, we're going to find out, aren't we? Cosine of 10. This quantity is 400, and we subtract from 400 0.2 times 406 times the cosine of 10, and that value is 80, right? So we get that the normal force between the floor and the wedge is 320 newtons. Well, now it's all over but the crying at this point, isn't it? So if we go back to here, we have this value, so we can solve this for P. So I'm going to bring P over to the right side of the equation because it's a negative on the left, so I'm just going to solve this. So I get 0.2 times 320 plus 0.2 times 406 times the cosine of 10 plus 406 times the sine of 10 equals P. So 0.2 times 320, that value is 64. Make sure I got all my signs correct. This is plus, yes. 0.2 times 406 times the cosine of 10. That value is 80 plus 80. And then my last term, which is also positive, is 406 times the sine of 10. And that number is 70. So I get 64. I get P is equal to 64 plus 80 plus 70. And that value is 214 and a half newtons.
I have a question.
Yes.
So when we approximate 70.5.
Yes.
It's just 70.5. Well, I just tried to convert it to 2 sig phase. It would be 71 then, or still 70? Would it make a difference?
Oh, I understand your question. That's a good question. You could leave it as 71.5, and then that 0.5 will stay in the final answer.
Like, would it be a big deal if I have like 71?
Absolutely not.
What's the maximum mistake?
It's a good question. Well, I don't even think it's a mistake, because if you really want to look at the numbers, the force that's exerted here at A is given as being 600 newtons with no decimal places, so that means that our actual answer is going to have one significant figure. So that means that if we were going to be very rigorous instead of writing P as 214.5 newtons, we would write it as 200 newtons with no decimal points. So,
That's the.
right. The thing I would not like to see is if you said that P was equal to 214.4962842.
No.
But yeah, but within a newton or so, so that's sort of, and you're not gonna lose a lot of credit. Other teachers, I would definitely ask that question, because like if you're in chemistry, this is like paramount.
Dr. Cuddy's like,
Sorry, you will not be forgiven for that mistake. So yeah, but in general, the real answer would be 200 newtons if we were really being rigorous with, but I just sort of feel like they really mean 600 point newtons, but I don't have any reason for that.
It's kind of backwards. We have to find an angle and.
Right, yeah,
So we have to find an angle.
yeah, it's quite a deal, isn't it? So, yeah, anyway, but the next question, the components of the corresponding reaction at B. All right, well, we already found reaction at B in the y direction. So we can find the reaction at B in the x direction. I'm not going to have you guys do that, but I'll just show the problem. If we're going to find the reaction at B in the x direction, we would say that we look at the machine part plus 600, and then it would be, let's see, here's my normal force acting, so that would be minus the normal force from the machine part in the x direction, and then the friction is actually going that way, so in the x direction that would be positive plus the frictional force of the machine part in the x direction. Those four things would equal 0. Then the frictional force, of course, is mu s times n mp x. So you just have that one unknown right there. And we know what that is because we found it right here. And you can substitute it in and finish that problem. All right. You guys, I ran out of time to talk to you about the final. So I'm going to do that really quick. How's that sound? And then I will post the problems, because you need to have 4 problems, but I don't have time to do that because I want to go through the book and make sure that I choose good problems, okay? So I will have that posted to our Moodle page right after this class. But the important thing to know is our final is scheduled for Friday morning from 7:30 to 9:30. And if you wish to take it at a different time, that is absolutely fine with me, but just set up a different time. If you are at a distance location and you wish to use a proctor, that's fine, but you need to tell me your proctor so that I can set up the information with them. If you want me to proctor you through Zoom, I'm open to doing that as well. So you just have to let me know a little bit ahead of time which way you want to go. The test will consist of 4 problems, and they'll each be equally weighted. And you can bring in a study sheet with anything in your own handwriting. So at the end of class today, I will put up on our Moodle page review problems for the final exam, and they'll be available to you. So in between now and the time you take the final, if you have any questions, just make sure that you let me know, and I will help you in any way I can. All right, you guys have a wonderful day.
Thank you very much.
And that's it, you guys. It's in the can.